Okay, first of all, calculating the magnetic field here. It's a fairly simple calculation because, as we observed, the QV is perpendicular to the R vector, so that the sine of theta is just 1. Theta is 90 degrees, sine theta is 1. So we just plug things in. We've calculated QV for our particle, and it's 4.8 times 10 to the negative 13th amp meters. And that calculation is done previously. Our K prime is 10 to the negative 7th Tesla meters per amp. Our denominator is the square of our R, the magnitude of our R vector, which is 10 centimeters, which is 0.1 meter. And having squared that, we get, well, this is going to be 10 to the negative second, just looking at the numbers. This is going to be 4.8 times 10 to the negative 20th. So dividing that by 10 to the negative 7th, we're going to get 4.8 times 10 to the negative 18th. And that should come out in Tesla, because Tesla is the unit of the magnetic field. But let's be sure. We have actually, maybe I've got the wrong units on K prime. Let me think that through again. Okay, lost track of the fact that I had a meter squared in the denominator. Okay, so in the numerator we have meters times meters, which is meters squared. In the denominator we have meters squared, so the meters go away. The amp in the denominator here divides into the amp in the numerator here. That goes away. We're left with just the unit Tesla. So this is our magnetic field. Now this is a magnetic field of just a single electron moving at a 10 to the 6 meters per second is pretty fast. We're actually moving at about 1/100th the speed of light. Turns out it's really easy to get electrons up to almost light speed. So that's not a particularly fast electron, but it's still got a significant velocity. If it's gone faster, if it's gone light speed or almost light speed, then you would have another factor of 2 here. You'd have 10 to the negative 16th Tesla. At a distance of 10 centimeters, now 10 centimeters compared to the subatomic scale is a huge distance. If we brought this down to, say, a micron, then we would have a factor of 10 to the negative 6th here, squared, which would be 10 to the negative 12th, and that would bring us down to like 4.8 times 10 to the negative 4th Tesla. So as we get down toward atomic scales, we start getting a very strong magnetic field. A Tesla, incidentally, is quite a strong magnetic field. Okay, in order to produce a force of 1 Newton on a 1 Coulomb charge moving at only 1 meter per second takes quite a strong magnetic field. So you kind of keep that in perspective. Okay, well, there are a couple other questions we want to address. I'm going to write a couple of things on the board. Okay, we want to do the calculation for the point 10 centimeters, 0. So point here in the XY plane at coordinates in the XY coordinates, 10 centimeters, 10 centimeters. So we're going to have to recalculate our vector R, but let's just conceptualize what we have first. Okay, what changes between here and here? Well, one thing that changes is this angle. What's this angle? You should think it through, but it's pretty clear that that angle is 135 degrees. And what's the R vector? The R vector is 10 centimeters times I plus 10 centimeters times J, which is 10 times the square root of 2 centimeters. Well, wrote that badly. I've got to fix that. The magnitude of R is going to be 10 times the square root of 2 centimeters. Okay, I've written what I intended. I put a centimeter into the square root, got ahead of myself on what I was writing. In any case, R is 10 centimeters I plus 10 centimeters J, which is very clear. And that's going to be written 10 square root of 2 centimeters. Now, why would I write 10 square root of 2 centimeters? Because that's the magnitude of this vector. And that's our R. Okay? Not our R vector, our magnitude of the R vector. Then I'm going to write that as multiplied by I plus j over the square root of 2, that being the r vector divided by its magnitude, which is the r hat vector, the unit vector. So now we have r expressed as a magnitude times a unit vector, and that's a very convenient thing to do, and I do recommend that. Now let's think about the direction of the cross product. Fingers in the direction of QV, turn them so that our fingers rotate through the XY plane over to the vector R, and our thumb is going to be down once more, so that the magnetic field, won't be able to draw it as long as I did before, but here's your magnetic field. It's vertically downward. Now let's see how that comes out of the calculation. Well, our calculation is very much like it was before. We have the same numerator until we get up to the vector. In other words, 10 to the negative 7th Tesla meters per amp in the 4.8 times 10 to the negative 13th amp, which might not be completely clear, but I think we got pretty good resolution here. But the distance down here, the magnitude of the r vector, is 0.1 times the square root of 2 meters quantity squared. Now, when we square that, we're going to have 0.1 squared, which gives us the 10 to the negative second we got before. But the 2 squared is going to give us a factor of 2 down here, so that this much of the calculation will come out 1/2 as great as it did here. And it's 1/2 as great due to the fact that this distance is square root of 2 times as great, so that when the distance is squared, it is twice the squared distance as opposed to here. The other part of the calculation, I factored the vectors out. I did something a little bit wrong up here, and I'm going to go ahead and correct it just so we get it right. It's going to be, this is actually negative, so that we get negative this many Tesla times J, and it's not J, it's K. So let me fix that and explain it before we go on. Okay, I was careless when I wrote this out. Obviously, our QV vector is in the direction of negative I, but of course I put the negative here, and that's okay. The negative this times I is our QV, and our R divided by R is our unit vector in the J direction. So that we have I cross J here, which gives us K. We have a negative here, so that the vector is in the negative K or negative Z direction. Okay, and that reconciles with what we got when we thought about our cross product here. Now, down here, I wasn't as careless, and it's a good thing because that helped me fix that little error. Okay, so what we get then, again, squaring 0.1 times the square root of 2 gives us half of what we got when we squared 0.1. So the denominator here, gives us twice what we got when we squared this. So we're going to get for the numbers half as much as this, just from this calculation. Okay. Then when we do I cross I plus J over 2, well, I cross I is 0, I cross J is negative K. I cross J is K. Okay. So we're going to get negative K, but it's going to be over the square root of 2. Well, what that gives us is 1 over 2 square root of 2 times what we got before. And it'll be negative 4.8 times, okay. We got a negative here because we have a negative here on the 4.8 times 10 to the negative 13th amp meters. And I don't know where my meters went to. Meters times amps, okay. So we get this. Now 2 times the square root of 2 is about 2.8. So this is going to be reduced by a factor of 2.8, giving us something like maybe 1.8 times 10 to the negative 18th Tesla times K. Now, you can check my arithmetic on that, but the main thing you want to see from this situation just is now the R vector is not perpendicular to the QV vector. The R vector is also longer than it was here. Now, the fact the R vector is square root of 2 times as long, as I said before, by itself would give you half of this. Okay? But then the fact that the R vector is not perpendicular to QV, but at an angle of 135 degrees with respect to QV, reduces the result again. And another way of seeing how that reduces the result is that the sine of theta is a sine of 135 degrees, which is the square root of 2 over 2. So multiplying half this by, half of this, which is what you get by this squared being twice what this square is, you then multiply by the square root of 2 over 2, and you again end up with the same result. So if we were to multiply by the sine of 135 degrees instead of calculating this cross product, we would still end up with the identical result.